In exercise 1 on page 69, we will look at the mixed Poisson process. Now, we have already worked with Poisson processes, and we all know what a Poisson process is. In particular, we know what a standard homogeneous Poisson process is. A standard homogeneous Poisson process is just a process where the increments in claim number are Poisson distributed with the same expected number of claims in a time interval as the length of that time interval, right? And we also recall from the earlier chapters that if I have a standard homogeneous Poisson process in tilde, and I decide to transform the time inside with, for example, some number, 5, then the thing here, what does this mean? Well, this means that I speed up the time of the standard Poisson process with a factor 5. So instead of expecting 1 claim per year as I do in the standard Poisson process, then here I will expect 5 claims per year, and then what I have is a homogeneous Poisson process with intensity 5 or mean value function 5t, right? Now the thing is, whenever I look at a homogeneous Poisson process, the number here, the number of the intensity, it tells me how many claims I can expect to arrive inside 1 time unit. So if the intensity is 5, I expect 5 claims to arrive in 1 year. Maybe 2 will arrive, maybe 10 will arrive, but on average I expect 5 claims to arrive per year. And then I can say, well, I can use this to model something. For example, if I just write instead 0.2, that would mean that I expect 0.2 claims to arrive per year. However, on the other hand, you can also say, well, this really assumes that you expect 0.2 claims to arrive per year for every single person you encounter. On the other hand, some people might say, depending on the population, then maybe you don't want to use the parameter 0.2 to model everybody, right? So let us try to look at what happens if we're trying to model different claim number processes for a population that isn't necessarily homogeneous. So let's say we have a population of men and women. I don't know how we're supposed to draw this. Shall we say this is a man and this is a woman? No, I don't know how to draw this. So we have a population of men and women like this. So 1 man, 2 men, 1 woman, another man, and another woman, and so on. And you're not really sure which one of these you'll have to look at, or how many of each you will have. However, you do know that in the case you encounter a man, then the total claim size the claim number will follow a homogeneous Poisson process, for example, with intensity 0.5. So on average, the men in this population have half a claim per year. So every 2 years we expect a claim to come in for this person. However, maybe the females are more careful drivers or drive less, who knows. But statistics might show us that on average they only have 0.2 claims per year, which means that 1 claim arrives every 5 years. So in this case, you will have to look at a population and say, well, what can I say then about my claim number process in general? And that is where the mixed Poisson process comes in. Because with the mixed Poisson process, what we consider is a transformation in time of a standard homogeneous Poisson process, where we then say, well, the theta that defines the intensity, which is like the 0.5 or the 0.2, so the thing that decides the average number of claims per time unit, is random. The theta can take on different values according to which outcome we have. In this example, for example, I have modeled a theta which can take on the values 0.5 and 0.2. If we have a more or less equal number of men and women, then we'd say that theta is 0.2 with probability 50%, and theta is 0.5 with probability 50%. Now, theta can be modeled in a number of ways. One way is to use it to model the, if to model whether or not we're encountering men or women. Another way is maybe to use it to model something else. So theta doesn't necessarily have to be a discrete random variable. It just has to be a random variable that has a finite variance and that is independent from our standard homogeneous Poisson process, and also will require that theta is positive. So whenever you see theta, just know that this theta is not a given thing. It is a random variable. Now, what do we want to do in exercise 1? In exercise 1, we want to talk a little bit about how the mixed Poisson process that looks like this, how it behaves. We will show a number of things. In A, we will show that a mixed Poisson process does not have independent increments. And in that sense, it is different from the traditional Poisson process. The next thing we want to show in B, however, is that a mixed Poisson process has one thing in common with the traditional Poisson process, and that thing in common is that it satisfies the order statistics property. And then in C, we will find out that n of t in the mixed Poisson process is not Poisson distributed. So its distribution, so the distribution of the claim numbers is not something that the mixed Poisson process has in common with the traditional Poisson process. And in D, we will look at an example of a mixed Poisson process where theta is gamma distributed. And we will conclude that in this case, the increments n of t, or the total number of, not increments actually, the total number of claims up until time t will be negative binomially distributed. And in that case, we will call this mixed Poisson process a negative binomial process. So these are the results that we will be showing in this exercise. And we will just do the solutions like A, B, C, D, one by one. And tackle things as we go along. One last thing just to end this video with is that in general, whenever we work with the mixed Poisson processes, we will often say stuff like, given theta, n behaves like a standard, like a homogeneous Poisson process with intensity theta. So this thing will, so this is something that we will use a lot. That given theta, so anywhere we have conditioned on theta, we will say that n behaves exactly like a homogeneous Poisson process with intensity theta. And that is a trick that we will be using quite often in this exercise. and you do not yet have the theoretical background to understand why we do that, but we will, however, be doing that.